In 2003, I was at the University of Newcastle on sabbatical, and while everybody else in the world was getting about 10 or 20 or 50 milliwatts per square meter, some brash young PhD student at Ghent University comes out with this paper showing 3,000 milliwatts per square meter. I thought, I gotta meet this guy. And so that guy is obviously Cornel Rabai, and he's been very active and influential in this field for many years, so I don't need to say anything more other than welcome, Cornel.
All right. Thank you very much, Bruce. Good morning, everyone. So, yes, Bruce at the time visited Ghent University, but I'm sure in the past years you have seen a different logo when I was giving a talk. So since last year I'm back at University of Ghent. So we're still in transition mode over there. Next to working in Ghent, because I love flying so much, I have a 10% position also at the recently founded Center for Microbial Electrosynthesis in Australia at the University of Queensland. So I'm hopping in between two jobs at different sides of the world. So thus far we have a small team where we're growing very quickly. This was the team that organized a week and a half ago the European ISMET meeting. Here you see the audience, about 180 people came, and we organized also a workshop the day before. And you recognize here maybe Falk Harnish teaching in the laboratory cyclic voltammetry. So that was a really successful meeting and a very good start for the organization. So what I'm going to talk about today is starting off a little bit different than most talks. I want to start first about fermentations. So fermentations are the cornerstone of bioproduction. You know, I once saw a documentary that says that beer saved the world. First, the production of beer apparently drove agriculture and drove trade and writing initially. As a Belgian, I can really live with that concept. So breweries and all kinds of fermentation exist for thousands of years, and you all know, I'm preaching to the choir here, that there's an enormous potential of using biomass through fermentations for all kinds of production processes. Now, the typical approach that we know for bioproduction is predominantly driven by pure cultures, so more and more engineered strains that give you a specific outcome and that reach very high concentration. Bioproduction runs at 100 grams per liter and more, with surfactants 400 grams per liter. That's amazing. Now, there's also a very well-known mixed culture fermentation, being methanogenesis, which is particularly in Europe, a very widespread, very well-established technology. Now, the thing with the exception of methane, typical mixed culture fermentations have an issue that they have low specificity. Like here you see the outcomes for fermenting sludge. You get a mixture of fatty acids. And there's typically low concentration. This is a graph that I once got from Bert Hamlers, and I need to chase up the reference, that shows you like the concentration of the product in solution and its value. And you can see that products that come in very low concentrations in a solution typically need to have a very high value because downstream processing is so expensive. So mixed culture fermentations suffer there. There is hope though. Here is some very nice work by Lars Angenen's group in which with long residence time fermentation you get the chain elongation happening. And so if you look at this graph from his paper in EES, you see that over time in their fermentations the caproate was almost the only product that was coming out of the reactor. So you can achieve over time quite specific product formation. I'll point out a disadvantage at this stage that I see of this technology is the quite extensive extraction needed. Downstream processing is always neglected. It's a very important, critical aspect of any production system. All right, but we also need to be, we don't just shoot at mixed culture fermentations. Pure culture fermentations also have their issue. You need to have very good process control. For example, oxygen distribution is critical to solve the redox unbalances that often occur during fermentations. Plus, of course, if you work with pure cultures, you need to sterilize. Typically, you run it in batch, and you still have quite some downstream cost to separate out the product. Now, this is where we believe that microelectrocatalysis, so the use of microorganisms to catalyze electrode reactions, can be very useful. So microelectrocatalysis thus far has been mainly used from a context of bioremediation. And there's two nice things that I want to point out here with two studies. This is work by Kelly Wrighton and Dino Virdis, where they inject nitrate in a reactor, and you can follow nitrate, you can follow current generation over time, and the metabolites. So you can have a very good control of a reaction if it's driven by an electrode. The second study is done by Howie Sheng when he was visiting us in Australia. And what he showed in this paper is that if you reduce nitrobenzene electrochemically, you get side products, while if you have a biofilm there, the nitrobenzene stoichiometrically goes to aniline. So you add specificity in the reaction. We always looked, we predominantly looked at these microelectrocatalysis, these kind of processes, not from a bioremediation perspective, but from a production perspective. So we can already quite effectively, at about 16 amps per square meter at liter scale, about 250 amps per cubic meter at pilot scale, take wastewater here from a brewery, but also for pulp and paper industry, and use that to drive a catalytic conversion at the cathode, for example, for sodium hydroxide production, but there's also peroxide, and the group of Terhane in the Netherlands looked, for example, at copper recovery as well. Now, you don't just need to run wastewater through an anode. There's much more interesting reactions, and this is a very elegant paper by the groups of Daniel Bond and Jeffrey Gralnick, in which at an anode they put a Schumanella onedensis, which they engineered to oxidize glycerol essentially and generate ethanol, and the electrode is taking care of the redox imbalance. So the big items that I wanted to thus far put forward is, with approaches like this, you can work on redox balances of fermentations. With approaches like the long-term fermentations with mixed population, you look at specificity. The key issue that we still need to think about is concentrations. One more point. So this was anodic. The study of Daniel Bond's group was fermentation at an anode. Known for a very long time is that you can also provide electricity to fermenting microorganisms in what they initially called an electro-energizing fermentation. And so through time, since the 70s, products like glutamic acids in 1987, it's a very rarely found paper of Greg Zykes. It's actually an abstract of the American Chemical Society. They looked at butanol fermentations, propionate. If you look at these studies, they had some issues. They needed mediators to to bring the electrons to the microorganisms. The organisms are quite arbitrarily selected, and the harvest of the product was not considered there either. So with that background, I want to today talk a little bit about what happens if you provide electricity to a mixed population. What products do you have? What organisms are evolving in such a system? And second, I want to explore whether we can achieve in-situ separation of the products via the electrochemical system. So the model compound we use to look at fermentations is glycerol. Glycerol at the moment costs about €200 per ton, crude glycerol. There's quite a lot of it. It's finding its way to the market. It's got positive market value, same price roughly as molasses at the moment. And if you're going to ferment it in a mixed population, there's quite a bit of outcomes that you can have, starting from this here glycerol. You have 1,3-propanediol, you can make propionate, propanol, all these different products. So what we wanted to do is feed glycerol to the cathode of a bioelectrochemical system over time and follow the products that you get and follow the microbial community. To do that, we used a system that we also presented in Leeuwarden a good year ago. This is a multi-anode or a multi-cathode, depending on how you use it, compartment. So we have a reactor with many removable small anodes. They're about 12 centimeters long, as you can see here. And so we can remove an electrode from the system and slot in a new electrode. And this way we can do time-based analysis. We calibrated this system, and this paper is soon to be published, with just a normal fatty acid fed anode. And what we got was a population dominated over 60% by geobacter, so that shows that it's the right way of running this system. And we took samples from many different electrodes, front, back, bottom, top. And so what we found is that if you take samples from one electrode, it can be regarded as representative for the microbial community. And we've also shown now that sampling doesn't have a major impact on the performance. So this system can be used for time-based analysis of microbial communities in bioelectrochemical systems. So then we got started by feeding a solution with more than 8 grams per liter of glycerol to a cathode. In that cathode, through the electrode, we pushed a milliampere per square centimeter, and we followed over time the metabolites that we have. And the first thing that you can see is that the metabolites you have are not necessarily constant over time. They are dynamically evolving, although you can see over time that 2 products here dominated very much the effluent. So to put it a bit more clearer, the key observations, like if you provide current to the community, you get this outcome. If you run an open circuit potential, you immediately get a drop in glycerol consumption. So current seems to drive faster glycerol consumption, even though glycerol is a donor. And you get also the formation of alcohols like propanol and ethanol. Now I find this interesting. This is a cyclic voltammetry, a turnover cyclic voltammetry for a bare electrode. And you see the hydrogen evolution reaction taken off at about minus 1.2 volt versus the reference. If you have an electrode with a biofilm growing on there, it seems that this hydrogen evolution reaction shifts upward around 400 millivolts. We also wanted to see, is this just hydrogen production? So we put a small electrode in the bottom of the reactor and provided hydrogen at the same flux, hydrogen gas at the same flux as the electricity inside the reactor. But hydrogen didn't make any impact there. It seems that current, if provided in situ, brings stronger reducing conditions, or at least conditions that change the output. But there is no specificity. So then on to the community that evolved there. So the first thing that we saw after inoculation, so the inoculum has a very diverse community from a fermenter. Very rapidly after inoculation, the diversity dropped very much in the reactor. So showing that this is quite a selective or quite a different environment to where the initial fermenter inoculum. And so initially the only organism that really maintained itself was a Citrobacter-like strain. Over time we saw a Pectinatus strain coming up, and later in the experiment also Clostridia. Now if you plot the key metabolites that you have over time with the key dominating organisms, you get actually some quite sensible relationships. Citrobacter species corresponds to 1,3-propanediol as the main outcome. Pectinatus species, the emergence of that also correlated to an emergence of a propionate, and then we have also later on the Clostridium corresponding to the emergence of valerate. So to us, this makes sense. The metabolite seems to correspond quite well with the key players in the community, although this is not a stable community. So we have Citrobacter initially, Pectinatus later in the process. Now, on the long term, we get a lot of valerate and also some butyrate. I just want to return for a second. So this is valerate. We get a bit of butyrate, and also here you have propionate. So valerate is really becoming one of the dominant products from the reaction. And so thus far, we can only make a hypothesis on how this valerate is formed in situ, because we haven't really tested the fluxes there. But it would make sense that what happens, the process that I mentioned earlier that Lars is working on, that chain elongation starts occurring in this community. And the type organism Clostridium cloiveri is very well known to link a carboxylate to an alcohol and then generate a longer chain via molecule via reverse beta oxidation. And so it would make sense to us that in this community, so here you see the end result, lots of propionate and valerate and a bit of alcohols, that organisms like Citrobacter and Pectinatus ensure the formation of propanol, propionate, acetate, and ethanol, and that via 2 different ways of reverse beta oxidation, these can then give rise to the formation of your valerate. And the butyrate would be formed in the same way, just with a typical chain elongation. So over time, you get more and more, we evolve more and more to a limited set of products, but very important then is also to think, can you get these products out? Now, if you link a fermenter to an electrochemical cell, to a cathode of an electrochemical cell, there's a few interesting processes that can go on simultaneously. Say the typical cathode reaction, if the simplest cathode reaction is reducing water to hydrogen gas and you make hydroxyl. So essentially you are increasing the pH. For a fermentation, that's very useful. To many fermentations, sodium hydroxide is added to control the pH and have more product formation. So if you link a fermenter to an electrochemical cell, you get control of the pH. If you use in this electrochemical cell an anion exchange membrane, the volatile fatty acids that you form, well actually the carboxylates that you form in the cathode, like acetate, like propionate, they're all negatively charged. They can migrate through such an anion exchange membrane towards your anode. And your anode is very acidic, so carboxylates entering the anode immediately are converted into the corresponding fatty acids, and those are the ones then that you could extract, and those are the ones you want on the market. It's actually not carboxylates that you need, it's the carboxylic acids from a bioproduction process. So, as a side step, you don't just need to do this in cathodes. This is an example of an anode where we run digestates and manure through anodes, and we can extract cations like nitrogen and potassium at quite high efficiency. So basically we can generate now a process that at 80% efficiency pulls out ions from anaerobic digesters, for example, that we can then recover. But back to the carboxylates. So we first ran a whole series of electrochemical cells to see whether we could effectively extract fatty acids. And so on the left graph here, you see different configurations with, without spacers. And at the current density of about 30 amps per square meter, you see that per square meter of membrane, you can pull almost 1.4 kilogram of acetate, in this case, per day. So that's a very high flux. And the coulombic efficiency, if you play correctly with all the ion balances, you can get this up to higher than 80%. On the right-hand side graph, you see a combination of 3 different carboxylates, being acetate, butyrate, and caproate. And the larger the molecule is, and this makes a lot of sense, the slower the migration through the membrane. Right? So how can you deal with something like that? Well, you just need to make sure that there are no other carboxylates there than the one that you really want. All right, so we can do this in an electrochemical cell, extract the products. The next step is then to create a fermenter. So we set up a fermenter to do chain elongation and link this directly to the electrochemical cell. And we run such a combined system, so that's the experiment. So we feed acetic acid and ethanol, and we look at the product outcome. And we also had a control reactor which had no in-situ extraction. The synthetic feed we used clearly did not work as well as Lars's reactor, but we could still see some modest production of butyrate and caproate in the process. We also had less accumulation of the acetate and the ethanol than in the control case. In the anode then, we achieved a solution that in this case, because there was still a lot of acetate present in the cathode, that was heavily dominated by acetic acid. So just to put the numbers together, the efficiency of extracting fatty acids at this stage were about 33%. So 1/3 of the electrons is used to extract the fatty acids. You have a power consumption of about 4 kilowatt-hour per kilogram. But very importantly, while in the control, to maintain the pH at 5.5, we had to add 6.9 millimoles of sodium hydroxide per liter reactor per day. In the experiment, it was only 1.6. So if you apply an electrochemical cell and all you do with that is control the pH, that makes it already quite interesting, not very economic. But then if on top of that you can extract the products, that is your bonus. All right, I seem to have gone quite fast. Daniel will be very happy because he needed more time. So electricity affects fermentation, and this can be done both oxidative and reductive. But thus far, if we use mixed population fermentation, you can see it's a dynamic community. It correlates all very nicely, but still it's functionally very dynamic. And so that is one of the big challenges with mixed culture fermentations, is really reach the stability and specificity. But a process like the caproate formation shows already that it is in principle possible. Why is it interesting to link these fermentations to an electrochemical cell? Well, the first thing is that you achieve the in-situ extraction of the acid and not the salt. I can't stress that enough. It's lactic acid that you want, not lactate. Lactic acid is the expensive product, but typical extractions are going to give you sodium lactate, which you then have to harvest again. And also you avoid the dosing of sodium hydroxide. If you have a typical fermenter in a biorefinery, adding sodium hydroxide is adding sodium to the water. Sodium is very problematic in biorefineries. It just makes that you can't recycle the water unless you install a reverse osmosis. And that costs you about, basically roughly around $1,000 per megaliter treated. So it's a very high cost to get rid of the sodium. If you use an electrochemical cell to control a fermentation process, you have no addition of the salts. Last thing, and you've seen this graph in Bruce's talk before, there's also a very good economic incentive to, for example, extract caproate. So just explaining this graph again, this is the product value for running 1000 amperes through a cell for a day. And so the power that you generate then can be worth something like $1. Sodium hydroxide can be around $20 level. And if we go into bioproduction, you go up to something like $120, $130 product value. If on this logarithmic scale you add for 1000 amperes the caproate extraction, you generate about $250, $260 worth of caproate per day. So you can, with an electrochemical cell, extract quite a high value of products for a low input of power. There's going to be other processes that are going to chew in the economics, of course, but the baseline, the starting point is very good that you can really afford further working on this. All right, I want to thank a few people that have enabled all this research at University of Queensland, Paul, Junkit, and Jean. At Ghent University, there's Tom Hannibal, Nina, and Stephen. And for the caproate work, we also got support of Lars. I want to make an ad still for the international meeting next year in Cairns, Australia. I know it's a long way off, but it's an excellent opportunity to see all your colleagues from Europe and your colleagues from the Asia Pacific. And lastly, quite shamelessly, I want to make an ad for postdoctoral positions that I have on a new ERC grant. So I'm looking to build a multidisciplinary team of postdocs around the theme of the interface between microorganisms and polarized surfaces. This is the website, and so if you're interested, you can contact me. I'll take any questions you may have.
Questions?
Assuming your anodes, your products is a mixture of several different compounds, do you plan to separate them, purify, concentrate? You show energy consumption 4-point-something kilowatt per kilogram. Does that energy include the energy consumption to further process the?
No, no. So that's just the energy of the cell. So I guess the key thing is to do something like make your, if you run the reactor properly, you should actually have your initial substrates no longer there and have a specificity of the end product. This is mixed culture fermentation. With a pure culture, you could have a pure, like an acetate outcome. But like if you run the caproate, like on the beer, like Lars's group does, you get almost exclusively caproate. And that's what you need to have. If you only have caproate there as a fatty acid, that's the one you're going to extract. But you can, because the anode is so acidic, you can volatilize the fatty acids from there, and then it is easier to fractionate them relative to have to fractionate from the solution. But the challenge is always getting sufficient purity in any process. Yeah?
So in your engagement process, some methanogenesis might be happen, so pH is every time low.
Yeah, so we run the anode very acidic, and then the cathode, it's easy to maintain that at 5.5 in this case. And methanogens don't like low pH in combination with high fatty acid concentration because you get free acid inhibition. So it makes it easier to run. And the anode is becoming acidic anyway, so you might as well make use of that. So the lower the anode is in terms of pH, the lower you can pull that cathode along.
Some acidophilic methanogen is in there, so after you operating to the cathodic operation, the biocathode operation, maybe methanogen is growing.
If you have acidophilic methanogenesis, but that's very slow, huh? I think that's very slow.
Very slow.
No
acid produced.
Yeah, well, in some cases we had methane, particularly in the beginning, but if you keep on maintaining a low pH with a lot of fatty acids, certainly, you know, if you have a temporal accumulation of compounds like caproate, which is quite bactericidal, you get rid of them.
Anything else? Yes, bud.
Yeah, that,
Did your analysis work? Did you look at just the biochemical on electrode, or did you also look at suspension?
yeah, it's actually, we looked at both. Yeah, I forgot to say that. And there were very similar populations, interestingly. Where are we? Here, so that's the electrode, that's the electrolyte. So it's both communities. There wasn't much of a difference between the communities there.
Okay, last question? Yeah.
I was just curious if you'd tried to maybe make a sort of meta flux analysis where you actually looked at tried to actually build a systematic model to look at how these different fluxes could be going from one organism to the next.
Yeah, that would be very interesting, huh? To really do a community-based flux analysis. We haven't done that. I also don't know if I can do that, but if I can get somebody to do that, that would be great. Are you interested?
Okay, let's thank our speaker again.